Hello, I'm Andy Cockburn, and this is work with my colleagues Philip Quinn at Google, Carl Gutwin at the University of Saskatchewan, and Chen and Suwanaposee at Canterbury. The message that I want you to take away is all in the title. We've examined how a psychological bias called the probability weighting function influences users' decisions to use or ignore assistive interfaces. Our results indicate that people tend to overuse bad assistance and underuse good assistance. Breaking down the components of the title, first, regarding interactive decisions, we're concerned with decisions around smart, assistive user interfaces. Interfaces that adapt their behavior or reform input to better assist the user. The decisions might be static and explicit, such as deciding to turn on or off auto-formatting. Or the decision might be dynamic and implicit, such as choosing whether or not to glance at text entry suggestions. Regarding probability, we're referring to the probability that a system's attempted assistance aligns with the user's goal, which we term congruency. Sometimes a system's attempt to assist will be congruent with the user's goal, improving their performance. But sometimes it'll be incongruent, such as incorrect suggestions, hindering performance. As the proportion of congruent behavior increases, the performance gains offered by an assistive interface increase from losses on the left to gains on the right. And here's the interesting theory of probability weighting. Prior work from psychology has shown systematic biases in the decision weight that people apply to events of different probability. People tend to overweight low probability events on the left and underweight high probability events on the right. The paper describes a bias metric that we devised to characterize user decisions. Essentially, we reframe predictions from the probability weighting function into a bias plot that looks like this, predicting overuse of assistive features at low probability of accuracy and underuse at high levels of accuracy. The experiment reanalyzed data from a previously published experiment. It involved a familiar word-snapping assistive feature in which selected text regions snap to word boundaries when a space character is crossed. As shown here in Microsoft Word, when the user's task is to select whole words, like the top line, word snapping assists the user. But when only part words need to be selected, such as the lower line, word snapping hinders performance, and users have to backtrack the cursor into the first word to disable it. Each participant completed a set of 10 text selections, using traditional letter-by-letter selection without the assistive feature, and the same 10 text selections using word snapping. The order of letter-by-letter and word-by-word was counterbalanced. Each participant then chose whether they would prefer to use letter-by-letter or word-by-word for a third repetition of the same tasks, and they then completed the 10 selections using that choice. Importantly, we controlled the proportion of text selections that were congruent with word-by-word in 20% increments from 0% to 100%. In the 0% condition, none of the text selections were congruent with word-by-word, so all users should reject it. And in the 100% condition, all of the selections were congruent with word-by-word, so all users should accept it. 90 subjects were assigned to one of the 6 levels of congruency in a between subjects manner, so 15 participants per level of congruency. On to results. First, regarding performance, the mean time for tasks using the letter-by-letter selection method was 2.3 seconds, shown in red. At 0% congruency, the word-by-word interface was much slower than letter-by-letter, and at 100% it was much faster. These results conform with our expectation that an assistive feature will offer losses at low levels of congruency and gains at high levels. Next, this plot shows each participant's decision to use word-by-word or letter-by-letter in the final set of trials. Decisions to use word-by-word are shown as filled dots. Letter-by-letter decisions are unfilled. The y-axis shows how much faster or slower the participant was using word-by-word than letter-by-letter in the first 2 sets of trials. Choosing to use word by word when it offers a loss, such as these items, represents overuse. Choosing to use the assistive feature even when it harms performance. And choosing to use letter by letter when word by word offers a gain, such as these items, represents underuse, or choosing to ignore the assistive feature even when it offers a performance benefit. This figure on the right shows our main results for bias. Bias is calculated by subtracting the proportion of decisions representing underuse from the proportion of decisions representing overuse. At 0% and 100%, there is little overall bias. At 20% congruency, the participants tended to overuse word snapping, choosing to use it when it hurt their performance. And at 60 and 80% congruency, the participants tended to underuse word snapping, rejecting it when it would have helped their performance. All of these results generally align with our hypothesized outcome. Why does this matter? We think that it's important that designers understand the existence of systematic biases in people's use of assistive interfaces. People will overuse features that are frequently inaccurate, harming their performance, and people will underuse features that are frequently accurate, missing opportunities for improving performance. This is important because assistive interfaces are becoming more and more prevalent, and sometimes they clash with one another. For example, here, having typed super V, the user can swipe right to accept the suggestion supervisor, or they can press space to accept the suggestion superb. But inspecting these suggestions is likely to consume more time than typing the remaining 4 characters. In terms of further work, so far we have the results from only a single study, so obviously replication is required to gain confidence in validity. But there are also important opportunities for generalizing beyond the static and explicit decisions that we have studied. In particular, we're interested in testing whether these effects generalize to dynamic and implicit interaction decisions, such as the use of text entry suggestions. To quickly summarize, we analyzed theoretical implications of the probability weighting function for interaction. We devised a new bias metric for assessing whether or not users' decisions conform with the probability weighting function. And we used the bias metric to analyze results of a previously published study, with the results conforming to the theory's predictions, showing overuse at low levels of accuracy and underuse at high levels. Thanks for listening.